Hi everyone. So today also we will discuss about the topological sorting. In my previous video, I have discussed about the topological sorting using DFS, depth first search. Today we'll talk about can we solve the same problem using BFS. Okay, so if you haven't watched my previous video, please check out, click on the I button, you will get it. Let me just give you the brief idea about the topological one more time. So this is the topological order of this graph. So for one graph, we can have multiple topological order. And what is the topological order is for every edge u to v, u should appear before the v in the order. Okay. And your graph should be a cyclic directed graph. All right. Graph should not have cycle and it should be directed graph. Now let me give you, okay, let us think about the BFS, okay, how we can solve the same problem using BFS and how you need to approach the problem. Let's say you are completely beginner, okay, you don't know how to approach the problem, okay, just try to focus on me, how I am thinking about the problem here. All right, so let's say you want to apply the BFS on this particular graph. In BFS, what we do? We always start from one node. Let's say we have source as 1. So you will insert 1 into the queue, right? Then you will pop the 1, you will print it outside, and you will insert all the neighbors of 1 into the queue. So all the neighbors of 1 is 4. You will insert 4 into the queue. Now you will pop the element from the queue and you will print it out. You will insert all the neighbors of 4 into the queue. So you will insert 5, then you will insert 6, then you will insert 7. This is our BFS. You will delete it, you will delete it, you will print it. Okay, fine. You will delete it, you will print it because there are no neighbors of 5, 6, and 7. So we are just directly printing them without inserting their child. This is our BFS. Now what you will do, you will check. Hey, still do we have some node which are not visited yet? Yes, 2 and 3. So you will insert 2 into the queue again, and you will pop the 2, you will print it, and you will say, hey, 2 has neighbor 4, but 4 is already visited. So don't insert 4 into the queue now. Fine. You will say, hey, 3 is still left. You will insert 3 into the queue and you will print it. Okay, and child of 3 is 4, which is already visited, so no need to insert it again. This is the BFS. All right, this is our BFS for this particular graph. Now, what is the problem with this and what is the difference between the topological sorting? So if you talk about the topological sorting of this graph, so 1, 2, and 3 should come before 4. But here 2 and 3 are coming after 4. It means direct BFS will not work. Why it is not working? Okay, because here we are not maintaining a condition that if all the parent of 4 are visited, then only you need to print the 4, not before that. So if we modify the BFS in such a way that it should handle the all the parents, it should have some value to keep track of, hey, all of my parents are visited or not. If they are visited, then only I will print myself. All right. So yeah, we can do that. So let me quickly explain you. Okay, 1 second. Let me clear out it. All right. So what I was saying is, let's say you want to apply the BFS. Now, before applying the BFS, here so here what we are talking about is, if can we store some information on each node just to keep track that, hey, all of my parents are visited or not. So parents are nothing but in degree on the particular node, right? So what is the in degree of 1? 0, right? What is the in degree of 2, which is again 0? What is the in degree of 3, which is again 0? What is the in degree of 4, which is nothing but your 3? right? What is the in degree of 5? 1. In degree of 6 is 1. In degree of 7 is also 1, right? So here in degree means how many parents you have, right? Perfect. Now, first of all, what you need to do? We will just insert all the node whose in degree 0 into the queue. So we will insert 1, we will insert 2, we will insert 3, because all of these are having in degree as 0. Now what you need to do? Again, apply the same logic of the BFS. So you will delete the first node of the queue, you will print it out. Now you will check all of its child, okay? But what you will see, once you will delete the one from the queue, you need to decrease the in degree of all of its child by 1, okay? What it means is, hey, you are just saying to your child is, hey, I got printed, okay? So I will not come to you now. So just decrease your in degree by 1. So once you will delete the 1 from the queue, you will print it. Then this degree of 3 will become 2 now. Great, right. Now you will not insert 4 into the queue unless its degree 0. So very important note. You will insert node into the queue only when its in degree is 0. Now we will not insert 4. You will delete the second element of the queue, which is 2. What you will do, you will print it, right? After printing 2, what you will do again, you will decrease the in degree of all of its child by 1. So its child is nothing but 2. So decrease the in degree by 1. It will be 1 now. Again, you will not insert into the queue because in degree is 1. We will only insert the node whose in degree is 0, right? You will delete 3 into the from the queue. You will print it. You will see. You will decrease the degree of all of its child by 1. It will be 0 now. Now degree of 4 is 0. So you will insert the 4 into the queue now. All right. So 4 we have inserted into the queue. Now 4 degrees also 0. Now once you will delete the 4 from the queue, you need to decrease the degree of all of its child by 1. So this degree of 5 will be 0 now. Okay, degree of 6 will also be 0 now. And degree of 7 will also be 0 now. Right? So you will insert now, what you will do, you will insert all of its child into the queue if their degree is 0. Yes. So 5 is also 0, 6 is also 0, 7 is also 0. And one by one you will delete, you will print them because they are not having any child. So no worry about that. And this is our topological order. So here you can see every parent we have printed before its child. So this is the all the 3 nodes which we have printed first, then we have printed 4, then we have printed 5, 6, and the 7. All right. So don't you think that we are using BFS? Only thing which we are maintaining is we are maintaining one in degree array for each node. For each node, we are maintaining the value of in degree. Okay. And first of all, you will insert all the node into the queue whose in degree 0, and you will keep deleting, and you need to insert node into the queue only when it's in degree 0. That's all. Very simple, right? So let me just give you one more example here. Here what we are doing. Let's say we have this graph 1, 2, 3, and 4. Now you will insert 1, 2, 3 into the queue. So your queue will have 1, then 2, then 3. Now you will you will delete the first element of the queue. You will print 1 here. Now you will you will decrease the in degree of all of its child by 1. So this 3 will become now 2, right? Yes. You will delete 2, you will print it out, you will decrease the degree of its child by 1, it will be 1 now. You will delete 3, you will print it out, you will decrease the degree by 1, it will be 0 now. Since 4 degree 0 now, you need to insert 4 into the queue, and this way you will get it. All right. So this is our topological order. So we will not waste much time. Let me quickly jump to the actual program of this one, which I have written in the Java language. So what we are doing, this is the how we form the graph. Okay. Now only thing which you need to do is when you are inserting the age into the graph, that time you can maintain the in degree. For each node, we will maintain the in degree. All right. Now how? We are saying there is one age from source to destination. It means we can come from source to destination. It means in degree of destination, we need to increase by 1. So we are increasing the in degree of destination by 1. That is the only thing you need to change into the graph declaration part. Now, you will do rest, everything will be same. You will create one graph object. You will insert the age into the graph. Then you need to apply the logic. What is the logic? We will take one queue. And in that queue, what you need to do is you will run a loop. Okay. And you will check. You need to insert all the node who's in degree 0. Just insert those into the queue. We are doing that. This visited logic is same as the BFS. Okay. So what we are focusing here is we are focusing about how to use in degree just to insert into the queue. So you will insert node into the queue only when its in degree is 0. All right. Then what you will do, you will run a loop on the queue until queue is empty. You will delete the first element of the queue, you will print it. Now, once you will print it, you need to decrease all of its neighbors degree by 1. Here we are doing that, you can see. We are running a loop just to get all of its child, and we are decreasing that degree by 1. You can see this minus minus will decrease the degree by 1. Now, after that, you will check, hey, after decreasing the degree, if current node in degree becomes 0, we will insert it into the queue. So we will insert it into the queue if its in degree become 0. Else we will not insert it. Now after this loop will come out, again we will check if do we have any node whose in degree 0, we'll simply insert it, else no need to insert it. Fine. So one more thing, so we can remove this part here. Why we are saying about that? So here, because we will only insert the child node, let's say. Okay, we will only insert the child node and we can see the child node degree. Now, what can be the issue is, let's say, it will work. It will not be a problem. Let us run it. We are getting it, right? So no need to insert one more loop because here only we are checking after decreasing the in degree, we are checking if in degree became 0, you need to insert it. So this is our topological order for this same graph, which we have discussed in my previous video. This is the graph. So 5 and 4 should come before 2, 0, 1. Okay. 5 and 4 should come before 2, 0, and 1. Yes, they are coming. And your 2 should come before 3. 2 should come before 3. And your 3 should come before 1. 3 should come before 1. Right? So this is your one of the topological order. All right. So if you want to take a screenshot, you can take it. I will add this code in my first comment in the video. So this is the code. You can take a screenshot. You can write by your own. All right. So thank you, everyone. If you like my content, please like, share, subscribe. Bye-bye, everyone.